Hello and welcome to the series on dots. In this part, we're going to look at the RMC Dots library that I've created, particularly around a feature for state machines inside dots. We'll talk a little bit about why you might need a state machine in your project, some of the challenges with introducing that, particularly in the dots world, and then how I've solved it. Let's start with some Unity Dots concepts. So Unity Dots is a library within Unity. It's a subsystem that is completely optional, and it's a very different paradigm to set up your projects. The benefits are performance, scalability, modularity, as mentioned here, and it really is rethinking from instead an object-oriented approach into a data-oriented design approach. There's three main parts. There's jobs, burst, and the ECS system that brings it all together. A bit about me, my name's Sam. I'm a game developer with over 20 years of game dev experience. The last decade or so shipping titles for all sorts of different platforms exclusively using Unity. Now, I'm newer to Dots because most of my Unity experience is with an object-oriented approach, or the game object approach of Unity rather. But here, we're going to be taking a look at Dots. My Unity OOP experience includes shipping lots of titles, as I mentioned. Some of them are listed here. I also do tons of education work around games, getting people into the industry and helping to level up their teams or their individual skills for new subsystems of Unity, new areas of game development. So I'm really excited to step more into Dots. During my own learning of Dots, which has been over the last year or so, I've shipped lots of different repos, sample projects. I've done game jams, and released a lot of videos that all have sample projects along with them that you see listed here. At the link you see listed, I've got all of this stuff brought together. So if you want to go to one URL and see this video as well as all my other stuff, you can go ahead and follow along with that there and check out different articles, repos that I've got, tips for using Dots. I'm still learning lots and I love to get feedback from the community. One of the key aspects of my Dots offerings is the RMC Dots library that I created that has maybe 15 or 20 different subsystems built on top of Dots and does a lot of the work for you. Now, I'm still learning my way through different Dots patterns, so as I work on projects, I add in reusable subsystems to this package we're going to look at today. And one of the newer ones that I've added is a subsystem around state machine logic. Let's start by taking a look at what state machines are, or what alternatives there are to state machines, and then bring it back into the Dots world and talk a bit more about it. So let's talk about structuring our AI behavior. Let's say that we have an enemy here. And for the purpose of this video, whenever I mention AI, I'm not speaking about generative AI, which is the hot topic, including ChatGPT and things like that. This is old school AI, which is mimicking intelligence within the behavior you have of your game objects. So let's say that we have an enemy here, and we're just going to talk through some very simple things you might want your enemy to do. And this is the demo that we're going to take a look at in code. So sometimes the enemy might need to move around. Sometimes the enemy might need to rotate or look toward the player or reevaluate the next waypoint. So there could be multiple different behaviors that you want to happen. Mutually exclusively is one of the ways that I like to think about it. So sometimes it's rotating, sometimes it's moving, but it's not doing both of them at the same time. For the sake of argument here, just to keep things simple. So how would we organize this type of behavior? Well, if you're beginning in game development, you might think about having the behavior in one script and you have a Boolean that says, am I moving? And if it's true, you do the move logic. And if it's false, you do the rotate logic. And if you add a third or fourth different thing it might do, then maybe you'd replace a Boolean with something else like an enum, right? That'll get you so far. But there's some challenges to the scalability of that. You might find doing that if conditional or that enum switch conditional throughout many different areas of your code base, and it becomes a challenge to add one more parallel potential behavior in there. So there's some alternatives that we can lean on from classic design patterns. State machines and behavior trees are a few of those options. They're really widely used. I'm going to read here. We've got these approaches are robust frameworks for managing complex AI behaviors, and it makes them indispensable tools that we can use. Developers like us can create even more sophisticated and responsive AIs by choosing one of these off-the-shelf solutions. There's some pros and cons to each of them, and like any new things that we learn in our game development journey, It is quite a bit to get into to understand how to set it up, how to implement it. Some of them require some third-party code you need to go and find or maybe recreate yourself. There is an investment there, but we always hope that this investment pays off. So let's compare the two approaches here. First is a state machine. You might have already heard of state machines, or maybe you're using them in your projects. So a state machine is about managing transitions between predefined states. So here's a little sketch of one that I found in an article I was reading. The pros of a state machine is it's really easy to implement. It's easy to debug and read through, especially for when you have simple set of states, like in our example of moving and rotating. It is a really nice approach. It helps separate your code out. It allows you to scale up and add more states down the road if you want. The cons is that it's not as scalable as the behavior tree that we'll see in a second, and it's less extensible. So in this chart, you can see that there's a responding, a running, a paused, a completed, and there's lots of lines between all of them. Each of those lines indicates a transition between the states. Now, if you have 5 states, you need to have a potential transition between every combination of those states. So with 5, it's doable. With 50, it becomes much less manageable to set up, and that may be where you would want to consider an alternative solution. One of those alternative solutions, super popular as well, is a behavior tree. So instead of a behavior tree saying, maybe I do this or maybe I do that, and I know exactly how to transition between those two, the behavior tree is a higher level hierarchical setup where instead of it just being this thing or that thing, you're able to tree out and plan the behaviors that you see. So let's just take a look at the diagram here. You can see that starting from the top, this enemy or player, whatever the behavior tree is about, would follow down through the tree, forking here and there, potentially doing sequences of activities or things in parallel. And each of them has a way to say, hey, I have succeeded in my step or I have failed in my step, and the tree responds. So you're really able to build out robust behaviors here. The pros are that it scales really well, that you can reuse across one project and between your projects a lot of these different modules. The cons are it takes a lot more to set up and it is less readable. One of the indications of its lack of readability is often behavior trees, let's say just within the Unity world, they ship with a way to view the behavior tree, maybe a node-based way to describe them in one window, or a special debugger window that helps you know which state you're in, or sorry, which of the behavior tree leafs you're in at any given moment. And while both of these two components could use that kind of visual logic, we often see it in the behavior trees because just reading the code is a non-starter. It's too difficult for you to be able to step through halfway into the tree, look at that chunk of code, and really get the big picture of where this fits in. So behavior trees certainly have a place, but for larger applications of AI in your game. So let's recap back where we were. So we have this enemy where sometimes it moves and sometimes it rotates. So what we could do, let's use the state machine setup. We could define each of those as a state, and we say that they are mutually exclusive. That means you're in exactly one of those at a time, but never doing both. And that's just a way to simplify this example. So we're either in the moving state, and we continue to be in the moving state, potentially forever, but periodically there could be a condition that's met that transitions over to the rotation state. So when we jump into the code, we'll be able to see an example of this. Now, the example we're going to look at will have about this many classes. So here's a class diagram showing. So starting at the top, here's our example scene, right? Inside of that, it has a state machine. The state machine is all of the states related to a specific thing. So here we've got our movement state machine that it's going to handle just the movement. And you can imagine in a game having many different state machines, perhaps for the player, another one for an enemy, maybe a more difficult enemy has a different one. So there's several different state machines that might be involved in your project. In this simple example, there's just one. And within the state machine, it's going to have a reference to 2 possible states. We are either in the translation state or in the rotation state. So let's say that we were in the translation state. Our game might have lots of other logic happening, but as far as this enemy or this character that we have, it is only in the state of translation or movement. So let's say that it's moving left and right, and it knows only about left and right. If you ever have a bug in your game around how that character is moving, you know naturally which class to go down and look at, right? You're not looking through several different if statements spread throughout your code base or several different switch statements on enums throughout your code base. You can really just drill down into this particular code. So it makes it very modular and easy for debugging. Now, an alternative would be that maybe there's some condition that's met and the state machine says, okay, now you're rotating. Again, it's only running that code. It's no longer running that translation code. And it's the state machine itself, at least in this particular implementation, that decides between those two states. Now, each state can say things like, I know when I'm done, or I know when we might want to switch to another state. But at least in my implementation here, it's the state machine itself that says, okay, the movement is done. Now maybe I want to rotate, and then it decides the rotation. So we'll look at that as well. Now, while in this example, we're going to be talking specifically about dots, I did want to give a shout out to some non-dots materials that I have. So here on this best practices page, it currently has OOP solutions in the best practices project there for how to do state machines in object-oriented programming and how to do behavior trees in OOP programming. So if you're excited about dots, but maybe you're not currently working on a dots project and you want to see how to handle similar solutions inside the OOP world, there's an amazing set of starting points here, including demos. So again, we're not going to be talking about that page right now. We're talking about the dots portfolio page. So here for dots stuff, you want to instead come and look at here. And one of the things that you can download is the dots library. And we're going to be jumping into that inside Unity today. So here I am inside Unity. Imagine I'm in the latest public release of Unity. What you would do is follow the instructions from that dots portfolio link and add the package to your project. Now I've already added it. Let's take a look at where it's at. So here in the package manager, I have the RMC Dots Library brought in. And there's a tab here for samples. And on that samples page there, you'll see a variety of different individual sets of samples. The one we're going to look at is the library demo, so we'll just be opening that one. But note that there's some other stuff that you could look at here. The point of the library demos is that for each feature that I include in the library, I have at least one sample scene that just shows a quick and dirty way to apply that. So we're going to be looking at the library demo for StateMachine. Here in the project, we can see the dots library demos folder. We've got lots of different demos covering most, if not all, of the features that I have in the library itself. Now you can imagine when you're sitting down to make a game, you could either bring in the dependencies to Unity Dots and recreate a lot of these different use cases, or take my library and either use directly the features that I've got, or maybe use them as inspiration for your own solutions. So for the state machine here, you could start out by fooling around with the example that we're going to look at today. And then if you decide to reinvent the wheel or improve it or customize it for your own needs, by all means, go for it. Sometimes within a given feature, like here within the state machine, I might have more than one demo. So here I've got what I call the light demo and then a full demo. We're only going to be looking at the full demo here. I'll mention a little bit when we get into the code what the difference is. First, let's take a look at the demo running. So here's the full scene. I'll check the sub-scene box here just to activate that and run the scene. And here we see our hero character, our player here, that is at times moving, and then it's rotating. And then it's moving, and then it's rotating, and we've got some console logs that just confirm that. Now you could imagine this could be much more behavior. You could have it be doing tons of different stuff. Patrolling for the character, looking for the next mission objective, checking out the different rooms that you have in maybe a world. Depending if it's your enemy or your character, you might be having it do lots of different behaviors there. Let's take a look at the code now. So on the right here, we see about all the classes that are involved in this demo. We've got an authoring component and the component itself. We've got a couple different states that we can step through, rotation and translation. We've got the state machine itself. But let's start here with this main, and I'm going to run it full screen so that I can now show the code a little bit bigger. So here we are in the mono behavior that just kicks off the scene. Now, like in most of my dots scenes, most of the work is done in the sub scene, but I always have a traditional mono behavior to, at the very least, do a debug log statement just to show what we're at. So down here, what I do is I set up the state machine. And as you're looking through these examples, I'm leaving comments that say state machine, comment 1, 2, 3, just to help me organize my own thoughts. And then if you download and check this out, you can step through those same comments. I might tweak them over time if there's something else I want to call out. But here what I want to do is from the monobehavior world or from some other scope outside of the state machine itself, I'll get a reference to the state machine, and then I choose what state to start on, right? There's lots of different things that could determine what state you start on. But right now, my state machine solution, which is a custom one that I created, doesn't have a way for a state to declare itself as a default. So what we do here is we request the state change and we pass in the state we want. So we're going to start moving here. So here we are in the state machine itself. Again, this is what's going to decide what states are possible to step into and handle any transitions between them. Note that when I say partial class and I declare my movement state machine system, that I extend the existing state machine system that comes from my library, and then I pass in which component it operates on. So right now, the core key to this system is you can have multiple state machines in your project, but each state machine operates on exactly one data component. And you can imagine that data component declaring, like it does in this case, how often should I rotate, how fast, how should I move? And here's the source code for that. You can see those values there. So I'll pop back and we'll continue to look at the state machine system that is running on top of this component. And down near the bottom there, you can see that the main responsibility here, you could have some additional logic, but it just declares which states are possible. So if we were to add a third state someday, we would register it here so that the system can know maybe I toggle into that third one. Now here we are in the state specific to movement, and notice that I extend my own movement base state, and we'll take a look at that after this one. Now, this one here, you'll notice that inside this update loop, some of the language in the API feels a little bit different, and that's because we're not running inside of the typical iSystem base or system base update with some of the available API that's there. It feels a little bit different here. This on update takes in a reference to the entity that we're operating on. So what you do here, it's almost like you're inside of a classic for each and you're doing some work on just one entity. So what this does here is it first just checks to see if this is a compatible component. Of course, it probably would be, but this also prevents any errors that happen below because these are the ones of the components that I'm going to be accessing. Then for those ones that I just checked on, I get those components. These are the things that I'm going to either be setting or getting depending on the needs of the particular operation I want to do. Then in this case, I'm operating that each of these states lasts a certain amount of time. That's completely optional. That's specific to this particular demo. But here, if we're not yet at the end of what the state should do, then I move the state along by, in this case, moving the translation component so that their object can float further upwards on the screen. Once the condition is met, this state says, hey, I think I'm done. It's time to consider a transition to the other states. You could have much more logic in here if you wanted to. And it's going to be handled by our base state that we've extended. So here we are in the custom base state that all of our movement and our rotation states extend. And this is going to extend one of the library classes that I've got. And here, the main thing you want to do is store any shared logic. Like in this case, I have the elapsed time in seconds for a given one of these states running. And then you want to handle those transitions between states. Let's see how we might do that. So again, a given state has called this saying, hey, I think I want to change. And here you can have very simple logic like this one that just says, hey, if I'm in state A, go to B. If I'm in state B, go to A. But you could imagine checking components, checking the state of them, saying, am I close enough? Saying, have I rotated enough degrees? You could ask lots of different questions. But the point is that here we handle that transition. Now, because this is the parent class of any given state, of course, a state could handle its direct transition to something else. But for the simplicity of this demo, both of these states just ask the parent state, hey, I want to change. How do you change? And that way I could centralize this logic because the logic is the same. If you're exiting one state, it does the same check if you're exiting the other state. So that's everything I wanted to cover in the demo. You can certainly download and check out the source. I didn't really get into the library code that makes all this work. I really just wanted to talk about how, as game developers, we can take advantage of it. So here's the scene running again. We can see that we are moving upwards, rotating a bit, moving upwards, and you could tweak how long it stays in any of those states. Inside the subscene is where this cube sits, the yellow cube, and I have the My Movement Data Component authoring sitting on there. That's a general dots convention for if you want to pass monobehavior serialized fields into a dots world, you declare them here. Now I've got one component that all it does is translate info about, well, when I'm rotating, how much should I rotate and for how long should I rotate? And the same thing for the translation system. So if I, for example, wanted to have them each rotate for 3 seconds at a piece and have them move quite a bit less than they are now, let's say I crank these values down a little bit, then I run the system. Now it will stay longer in each one and it will move more slowly. So here's 3 seconds of rotation, 3 seconds of movement, and you could imagine all the different complexity you would have on top of different enemies being able to tweak their values in this way. You could store these configuration values somewhere else, but I find this is a general convention that you put a game object in a subscene on the authoring component, you declare the values that you want there, and for simple use cases, I think that's a great fit. That's all for this video. We've talked a bit about state machines and the alternative of behavior trees, a little bit of the pros and cons of them. For our simple example, we've covered that we want a state machine and we want to do it inside dots, which is a uniquely challenging area to bring some design patterns in. A lot of the classic design patterns, including these ones that we're talking about today, are designed with OOP in mind. So when you bring them into a data-oriented design setup like Unity Dots, some of them just don't really work. Some of them work, but maybe it's a misusing of the data-oriented design system. I feel a bit as I was generating this, I was trying to jam the OOP concept into Dots and kind of make that system and the API for how that system works, kind of force it in there, so to speak. But I think as I'm learning Dots, part of the challenge is translating the game design fundamentals that I have and the OOP programming chops that I've got, bring them into data-oriented design. Now, if I was to use this in a production game, maybe down the road, I would realize this is not an appropriate solution because I want to do something more Dots-centric. Or I might recognize that the value gained here by bringing an OOP system and making it work in data-oriented design is so worth it that you can balance the pros and cons here. And I think that describes some of the push and pull that I've had when I've been learning Dots. I've spent hundreds of hours inside Dots creating a bunch of different simple games, but complete games so far. Really like it, what I'm in there. Of course, one of the major benefits of using Dots is the screaming fast speed that you get for your end users, right? You're able to run a higher frame rate on a lower powered device, pushing more graphics, doing more computation. It's super exciting, but it is a very different way to approach your projects. So thanks for following along here. I'm available for remote contract hire. You can always check me out there at that link. And please, I invite you again, I'll put the link below. Check out that Dots portfolio. Look at the other videos we've got, including some master classes on getting set up in Dots and some advanced things that you can do. Thanks.